Since the beginning of civilization, humans have gazed upward at the night sky with an insatiable hunger for answers. Our species is defined by exploration, from crossing oceans to reaching the moon, and now extending our dreams toward the stars. But among all questions about the cosmos, one stands apart in its enormity. Can we ever reach the edge of the universe? This question is not just about distance, it's about the very nature of reality itself. The allure of an edge implies a boundary, a final frontier where existence ends and the unknown begins. It taps into a primal curiosity within us, the desire to find limits, to measure our place in the infinite, and to conquer the seemingly unconquerable. The idea of journeying to the universe's edge is thrilling, because it represents ultimate discovery. Yet the truth may be more complex and far more humbling. Not only are we unlikely to reach such an edge, but the very concept of one may be a paradox. When people ask whether humans can ever reach the edge of the universe, the first problem that arises is defining what the word edge even means in this context. In everyday life, an edge is something concrete. It is the rim of a table, the boundary of a field, the cliff where land abruptly stops and air begins. Our minds naturally want to apply the same notion to the universe, assuming that it must have a border we could approach if we traveled far enough in one direction. But space does not behave like the landscapes we are used to. The universe is not a finite room with walls. It is an expanding fabric of space and time that stretches in every direction without obvious boundaries. Asking about its edge forces us to confront the difference between what we can observe and what might actually exist beyond our observational limits. What we often call the edge is really the horizon of our vision, a boundary defined not by physical walls, but by the finite speed of light and the finite age of the cosmos. Because light travels at a limited speed and the universe has existed for a finite amount of time, about 13.8 billion years, we can only ever see as far as light has had time to reach us since the birth of the cosmos. This limit is called the observable universe. It forms a kind of bubble around us, a spherical region from which light has had just enough time to arrive. Beyond that sphere, there may be more galaxies, more matter, perhaps even regions unimaginably different from ours. But we will never see them because their light has not yet, and in many cases will never, reach us. Thus, one definition of the edge is not a wall in space, but the limit of visibility, the boundary of what we can measure, detect, and study. Yet, the observable limit is not the same as the boundary of space itself. Space does not necessarily end at the edge of what we can observe. In fact, all evidence suggests that the universe continues beyond it. It might even extend infinitely, with no endpoint at all. If that is true, then searching for a literal edge is like trying to find the end of a line that has no endpoint, or the edge of a sphere by walking endlessly on its surface. You never encounter a boundary, because the system curves back on itself or stretches endlessly forward. This means that when people speak of reaching the edge, they may actually be seeking something that does not exist in a physical sense. But what if the universe is finite, not infinite? Even in that case, an edge may not look like a wall. One possibility is that space could be closed in shape, like the surface of a sphere. If you traveled far enough in a straight line in such a universe, you would eventually loop back to where you started, without ever crossing an actual edge. In this case, the boundary is an illusion of geometry. There is no cliff to fall from or wall to collide with. Space simply folds back on itself, endlessly continuous, tricking travelers into circling forever. This challenges our intuitive sense of direction and boundaries, reminding us that human experience of edges on Earth does not translate well to cosmic scales. Another complication arises when we consider the role of cosmic expansion. The universe is not static, but stretching in every direction. Galaxies are carried away from one another by the expansion of space itself, not by moving through space like ships in an ocean. This expansion means that what we call the edge today will be different tomorrow, because the horizon of what we can observe shifts as light from slightly more distant galaxies finally reaches us. However, because of the accelerating expansion of the universe, driven by dark energy, many of these galaxies are moving away faster than light can bridge the growing gap. This ensures that entire regions of space are forever slipping beyond our observable reach. So, the edge is not just a static line, it is a moving target, receding faster than we could ever chase it. The philosophical question then is whether an edge that can never be reached or seen truly counts as an edge at all. Some scientists argue that the universe's edge is a misnomer because it implies a tangible border, something definitive and finite, when in reality, what we have is a limit of perception. Our cosmic horizon acts like a fog. It is not that the road ends, but that visibility is permanently cut off beyond a certain point. In this sense, the edge is within us, tied to the nature of light, time, and the structure of space-time, not to an external wall marking where existence stops. If we accept this distinction, then the concept of reaching the edge becomes less about physical travel and more about stretching the boundaries of observation. Every new telescope we launch, every improvement in detection technology allows us to push a little closer to the horizon. We can peer deeper into the past, catching light that has traveled for billions of years. Yet we remain confined within the bubble of what light has had time to show us. This reveals a profound truth. Even with infinite determination, human beings may never encounter the edge of the universe in the way we encounter the edge of a continent. The cosmos does not have edges in the way our imagination craves them. Still, this realization does not diminish the grandeur of the quest. On the contrary, it elevates it. Knowing that the edge is not a place we can physically reach, but a shifting boundary defined by cosmic rules, forces us to see the universe in a more abstract and humbling way. The edge becomes a concept, a horizon that defines the limits of our understanding, forever encouraging us to push further. It also sets the stage for the deeper mysteries that follow, mysteries tied not only to light and perception, but also to the very forces shaping the cosmos itself. And to understand why humans will never reach beyond those limits, we must now turn to the idea of the observable universe itself, the bubble of reality that contains all we can ever hope to see or measure. The observable universe is one of the most fascinating concepts in cosmology because it defines the stage on which all of human knowledge about the cosmos takes place. To grasp it fully, we need to remember two fundamental truths. The universe has a finite age, and light has a finite speed. Light is unimaginably fast, about 300,000 kilometers per second, but it is not instantaneous. It takes time for photons to cross space. When we look at the Sun, we see it as it was about 8 minutes ago. When we look at the Andromeda Galaxy, we see it as it was over 2 million years ago. Extend this principle to the entire universe, and you realize that everything we observe is not a view of the present, but of the past. The farther away an object is, the deeper into time we are peering. Since the universe is about 13.8 billion years old, the maximum distance light could have traveled to reach us since the beginning of time sets the limit of our observable universe. At first glance, one might assume this distance is simply 13.8 billion light-years in every direction, but the reality is far stranger. Because the universe itself has been expanding during all that time, the objects that emitted the light we see from the early universe are now much farther away than they were when the light began its journey. This means the current radius of the observable universe is actually about 46 billion light-years, making the full diameter about 93 billion light-years across. This region forms a vast bubble centered on us, not because we occupy a special place in the cosmos, but because every observer, no matter where they are, sees their own observable universe centered around themselves. In this way, the observable universe is deeply personal and local. It represents the portion of the cosmos connected to us by light. It is crucial to understand that the observable universe is not the whole universe. Beyond its limits, space may continue indefinitely. There could be galaxies, clusters, and structures so distant that light from them will never reach us, no matter how long we wait. This is because cosmic expansion is stretching the fabric of space faster than light can traverse it. The consequence is profound. The observable universe is not just a practical limit of what we can currently see. It is a permanent horizon that will never move aside. There are regions of the cosmos forever hidden from us, not because our technology is insufficient, but because the laws of physics forbid their light from ever catching up to us. Within the observable universe, we find all the cosmic structures we know: galaxies, stars, nebulae, quasars, pulsars, black holes, and the relic glow of the Big Bang itself, the cosmic microwave background radiation. This radiation is particularly important because it represents the oldest light we can detect, a faint echo from just 380,000 years after the universe began. Before that time, the universe was so hot and dense that photons could not travel freely. Thus, the cosmic microwave background marks the ultimate wall of visibility, the farthest snapshot of the cosmos that light can provide. Beyond it lies the unseeable epoch of the early universe, hidden behind a veil of opacity that no telescope can pierce. The concept of the observable universe reshapes how we think about exploration. Humans may dream of traveling to other stars or galaxies, but the observable universe reminds us that there are hard boundaries written into the structure of space-time. Even if we mastered intergalactic travel, which is already far beyond our technological imagination, we would still remain trapped within this bubble of light. It is not a matter of determination or endurance. It is a matter of physics. Just as a fish in a bowl cannot see beyond the glass, we cannot observe beyond the cosmic horizon that defines our universe. Yet, this limitation is also what makes the observable universe so awe-inspiring. Within this bubble lies enough wonder to fill countless lifetimes of exploration. There are an estimated 2 trillion galaxies inside it, each with billions of stars and potentially billions of planets. The sheer diversity of cosmic environments, from blazing quasars to cold interstellar voids, offers endless mysteries. And while we may never reach the literal edge of the observable universe through travel, we can reach it conceptually through observation, continually refining our picture of what exists within our cosmic neighborhood. Every new telescope, whether orbiting Earth or placed on the far side of the Moon, pushes the boundary of detail, giving us clearer glimpses of the structures brushing against the horizon of visibility. But this also highlights the bittersweet truth. As powerful as our tools may become, the observable universe always defines a cage around us. We may stretch against its bars, but we cannot escape them. And even within that cage, time itself works against us. The more the universe expands, the more distant galaxies slip out of sight, redshifting until they disappear entirely. One day, in the far future, only the closest galaxies will remain visible, and the larger cosmic structure will vanish from view. In a sense, the observable universe is shrinking in what it can reveal, even as it grows in size. This means that our generation lives in a privileged era, a time when the universe is still full of light and galaxies to study before the curtain of darkness falls. To appreciate why this observable boundary is so rigid, we must now turn to the laws of physics themselves, which dictate that nothing can outrun light. This immutable truth forms the next wall of impossibility in our quest for the cosmic edge, the speed of light barrier. The speed of light is not just a fast number written in physics textbooks. It is the ultimate cosmic speed limit, the very ceiling of motion permitted by the laws of nature. At approximately 300,000 kilometers per second, it is so blisteringly quick that in a single second, light can travel around Earth more than 7 times. Yet for all its swiftness, this speed becomes a prison when we think on cosmic scales. Even at light speed, it would take over 4 years to reach the nearest star beyond our Sun, and hundreds of thousands to millions of years to reach most galaxies in our neighborhood. And this is only the beginning of the problem. According to Einstein's theory of relativity, nothing with mass can ever achieve, let alone exceed, the speed of light. The reason is not just technological limitations, but the very structure of reality itself. As an object accelerates closer to the speed of light, its energy requirements skyrocket. Each incremental increase in speed requires disproportionately more energy, and the closer one gets to light speed, the more infinite this demand becomes. At 99% of the speed of light, the energy needed is colossal. At 99.999%, it is nearly unimaginable. At 100%, the requirement becomes infinite, something the laws of physics do not allow. This is why photons, the particles of light, can travel at this ultimate speed. They are massless. Everything else, from spacecraft to humans, carries mass, and that mass anchors it forever below this ceiling. In practice, this makes the dream of traveling across the universe not just improbable, but fundamentally impossible. The restriction imposed by the speed of light is not just about propulsion. It defines the very fabric of space-time. Relativity weaves together time, space, and motion into a single framework where the faster you move, the more time dilates. At speeds close to light, time for the traveler slows dramatically compared to those at rest. This time dilation means that, theoretically, a ship traveling near light speed could reach distant galaxies within the crew's lifetime, as less time would pass for them. But this does not solve the larger problem. For those left behind, millions or billions of years might have passed, and the universe itself would have changed drastically in their absence. Worse still, even this relativity loophole cannot bypass the fact that no object with mass can actually hit light speed, and so any destinations lying billions of light years away remain completely out of reach. To understand the barrier more fully, consider how information itself is bound by the same rule. No signal, no message, no causal influence can travel faster than light. This is why distant parts of the universe are causally disconnected from us. Their light has not had time to reach us, and no signal from us can ever reach them. The speed of light is the ultimate traffic law of the cosmos, one that applies not only to matter, but to thought, communication, and influence. We can imagine fantasy scenarios of faster-than-light travel, such as warp drives, wormholes, or hyperspace jumps, but these require breaking or bending the very equations that describe reality. Every attempt so far, even in theoretical physics, runs into paradoxes or demands exotic conditions, like negative energy, that may not exist in nature at all. This cosmic barrier is why the dream of reaching the universe's edge collides with a hard wall. Even if we could build a craft that pushed the boundaries of engineering, approaching 99.9% the speed of light, the distances involved are so great that reaching even the edge of the observable universe would still take longer than the current age of the cosmos. And the cruel irony is that while we travel, the universe itself continues to expand, dragging our destination farther and farther away. The speed of light limit is not just a technological problem. It is a fundamental lock built into space-time, one that no amount of determination can pick. This is what makes the cosmic speed limit such a humbling concept. It is not just about what we cannot do. It is about what reality itself refuses to permit. Light is both a messenger and a jailer. It delivers the universe to our eyes across billions of years, but it also walls us into our cosmic neighborhood, preventing us from ever stepping beyond certain horizons. To truly grasp why humans will never touch the edge of the universe, we must go beyond just the idea of speed and look at the deeper structure of space itself. The speed of light barrier sets the rules, but the expansion of the universe rewrites the very board on which those rules are played. It is to cosmic inflation and expansion, the restless stretching of space-time itself, that we must now turn, for it reveals why even light cannot overcome the growing gulf between us and the unreachable edge. The speed of light sets the ultimate limit for how fast anything can move through space. But what makes the cosmos even more puzzling is that space itself does not play by the same rules. While nothing can travel through space faster than light, space can expand faster than light without breaking any physical law. This is one of the most counterintuitive aspects of cosmology. The fabric of the universe itself is stretching, and in doing so, it can carry galaxies away from us at apparent speeds that exceed the cosmic speed limit. This idea becomes even more remarkable when we look at the earliest moments of existence during a period known as cosmic inflation. Cosmic inflation refers to a breathtakingly brief yet transformative moment just after the Big Bang, when the universe expanded exponentially in less than a trillionth of a second. Imagine something smaller than an atom ballooning into a vast cosmic stage, large enough to eventually house galaxies, stars, planets, and life itself. Inflation is not just speculation. It helps explain several puzzling features of the cosmos, such as why the universe appears uniform in every direction and why its geometry is so nearly flat. But one of its most profound consequences is that regions of the universe were separated from one another faster than light could ever connect them. This means that even from the very beginning, vast portions of the cosmos became forever disconnected from our view, cut off not because of physical barriers, but because space-time itself stretched too quickly for light to bridge the distance. What inflation began, cosmic expansion continues. The universe has not stopped growing since that first burst of acceleration. At first, the expansion slowed under the pull of gravity, but billions of years later, it began speeding up again, driven by a mysterious force we call dark energy. As a result, distant galaxies are not just moving away from us, they are being carried away by the flow of space-time itself, and the farther they are, the faster this recession speed becomes. Some galaxies are already moving away from us faster than light because of this expansion. Their light, emitted today, will never reach us, no matter how long the universe endures. These regions are sealed off from us forever, like islands vanishing behind a tide that rushes faster than even light can swim. To understand how strange this is, picture a loaf of raisin bread rising in an oven. The raisins represent galaxies, and the dough represents space itself. As the dough rises, every raisin sees the others moving away, and the farther apart they are, the faster they recede. There is no center to the expansion. It is uniform everywhere. Now imagine that the dough rises so quickly that some raisins disappear from view altogether. That is what is happening in the real universe. Galaxies at the edge of our observable horizon are being pulled away so fast that their light cannot keep pace with the stretching fabric of space. This has profound consequences for exploration. Even if we built ships capable of traveling at nearly the speed of light, we could never catch galaxies beyond a certain distance. As we speed toward them, the space in between us and them expands even faster, stretching the gap endlessly. The universe itself conspires against us, ensuring that certain destinations will forever remain out of reach. This is not a temporary setback or a technological hurdle. It is a permanent feature of reality. The expanding universe has drawn an invisible line in the sand, beyond which nothing we do can carry us. What makes this even more humbling is that the line is not fixed. It changes over time, and with every passing moment, more galaxies slip across it. Today, we estimate that there are about 2 trillion galaxies within our observable universe. But as the expansion continues, many of these will eventually redshift beyond detectability. Far into the future, the universe will appear emptier and lonelier, with only the closest galaxies still visible. Entire cosmic histories, written across billions of light years, will vanish from sight as if they never existed. This shrinking of the visible universe highlights the urgency of studying it now, while the light from those distant objects is still reaching us. The fact that cosmic expansion operates beyond the speed of light reveals why the edge of the universe is not just unreachable, but constantly receding. Even as we look out toward the limits of what we can see, the true frontier of the universe moves farther away. Inflation and expansion have built a cosmos where edges are illusions, horizons are shifting, and distances are more than just meters or light years. They are ever-changing gulfs that grow wider the longer we wait. This realization brings us to another great puzzle of cosmology, one closely tied to inflation and expansion: the horizon problem. It asks why different regions of the universe, separated by distances that light could never bridge, appear so remarkably uniform. Understanding this paradox not only deepens our sense of wonder, but also underscores how permanently disconnected so much of the universe will remain from us. The horizon problem is one of the deepest and most thought-provoking puzzles in modern cosmology, because it forces us to confront the strange relationship between distance, time, and the limits of connectivity in the universe. On the surface, the problem begins with a simple question: how is it that regions of the universe that are impossibly far apart from one another, so far that light has never had enough time to travel between them, still look so remarkably similar? When astronomers measure the cosmic microwave background, the faint afterglow of the Big Bang, they find that its temperature is astonishingly uniform across the sky, differing only by tiny fluctuations of 1 part in 100,000. This uniformity implies that distant parts of the cosmos must have once been in contact, exchanging energy to equalize conditions. But according to the limits set by the speed of light, those regions should never have interacted. This is the horizon problem. Regions of the universe beyond one another's cosmic horizons behaving as if they were once connected, when by the rules of relativity, they should not have been. To understand why this is so perplexing, imagine standing at opposite ends of a continent and trying to keep your campfires burning at exactly the same temperature without ever being able to communicate. That is what the universe seems to have done. Points on opposite sides of the sky, separated by billions of light years, appear to have coordinated their states, even though there was never enough time for light or information to travel between them in the early universe. The only way this can make sense is if, at some earlier epoch, those regions were much closer together, so close that they could indeed share energy and come to equilibrium, before being flung apart faster than light by cosmic inflation. Inflation provides the solution by proposing that the universe was once an unimaginably small connected space that expanded in a blink, stretching those once neighboring regions far beyond one another's horizons. But even with inflation's explanation, the horizon problem points to something fundamental. Much of the universe is simply beyond our reach, not just practically, but in principle. Horizons are more than observational limits. They are barriers written into the fabric of space-time itself. As the universe expands, Galaxies beyond a certain distance cross a threshold where their recession velocity exceeds the speed of light. Beyond that point, they are permanently removed from our influence. No spaceship, no matter how advanced, could ever catch up, because as you move toward them, the space between you and them stretches faster than you can close the gap. They are not just far away, they are unreachable, sealed off by the very dynamics of expansion. This cosmic horizon keeps redefining what is accessible and what is not. Every second, more galaxies slip beyond it, carried away by the accelerating expansion driven by dark energy. From our perspective, the universe becomes a constantly shrinking stage. Though its true size may be infinite or at least unimaginably vast, the part we can ever hope to interact with grows smaller relative to the whole. The horizon is not a fixed boundary, like a fence we might one day cross. It is more like a receding shoreline that pulls away faster than we can swim. The harder we try to reach it, the farther it recedes, ensuring that we will always remain confined within our bubble of observable reality. For human exploration, this is the final blow against the dream of reaching the edge of the universe. The horizon problem shows us that the universe is not a playground we can conquer given enough time and technology. It is a realm divided by unreachable domains, islands of reality we can see only faintly, and even then only briefly, before they vanish into the darkness forever. These unreachable regions are not merely distant, they are causally disconnected, which means no action we take, no message we send, no engine we ignite will ever influence them. They might as well belong to a separate universe entirely. The horizon problem thus reinforces the humbling truth that the cosmos is far larger and more mysterious than we can ever experience directly. It reveals that limits are not just technological but fundamental, dictated by the rules of relativity and the restless expansion of space itself. And as we confront this reality, it naturally leads us into the question of what force is driving this relentless acceleration, pulling the universe apart faster and faster. That mysterious driver is dark energy, a phenomenon so strange and elusive that it reshaped modern cosmology and continues to baffle scientists today. Dark energy is perhaps the most mysterious player in the cosmic drama, a force that we know exists because of its effects, yet whose nature remains almost entirely hidden. It makes up roughly 68% of the total energy content of the universe, outweighing both normal matter, the stars, planets, and atoms that make up everything familiar to us, and dark matter, the invisible scaffolding holding galaxies together. And yet, unlike matter or radiation, dark energy does not clump, shine, or interact in ways we can detect directly. Its defining feature is its effect on the expansion of the universe. It accelerates it, relentlessly stretching space faster and faster, driving galaxies away from one another in a race that no force seems able to stop. The discovery of dark energy came at the end of the 20th century, when astronomers studying distant supernovae expected to find evidence that the universe's expansion was slowing under the pull of gravity. Instead, they found the opposite. The expansion was speeding up. This revelation was shocking because it suggested that some unknown energy permeates the fabric of space itself, exerting a kind of negative pressure that pushes everything apart. It was not enough that the universe was expanding, a consequence of the Big Bang. Now, it was expanding at an ever-increasing pace, as though an invisible hand were pulling at the threads of space-time itself. What makes dark energy so devastating to the dream of reaching the universe's edge is that it ensures the cosmic horizon is not static. With every passing moment, more galaxies cross beyond the limit of reachability. Their light stretches, redshifting until it vanishes from view entirely, as if they were erased from existence. In the distant future, billions of years from now, all but the closest galactic neighbors, will have disappeared beyond this horizon, leaving a night sky far emptier than the one we see today. Future astronomers, if humanity or its descendants endure that long, will not even know about the grand cosmic web of galaxies that once defined the observable universe. Their horizon will be a narrow shell, a shrinking bubble of visibility confined to their local group of galaxies, while the rest of the cosmos lies hidden forever. Dark energy creates a paradox of perception. The more we strive to understand the universe, the more of it slips beyond our reach. It also forces us to rethink what the word universe even means. Are we speaking only of the observable patch visible today? Or are we including the vast, unreachable regions being pulled away faster than light? If the latter, then we must accept that most of the universe is not only unseen, but will forever remain unseen, disconnected from us not by distance alone, but by the inexorable expansion of space-time itself. From a physical standpoint, one of the most unsettling aspects of dark energy is that it appears to be tied to space itself. Unlike matter or radiation, which dilute as the universe expands, dark energy maintains a constant density per unit volume of space. That means that as space grows, the total amount of dark energy increases. The more the universe expands, the more dark energy there is to fuel further expansion, leading to a feedback loop of acceleration. This runaway effect is what ensures that galaxies recede faster and faster, crossing horizons from which their light can never return. For exploration, this is the ultimate undoing of human ambition. Even if we could build ships that traveled near the speed of light, we would always be trapped within a shrinking cosmic bubble. The expansion rate of the universe grows too powerful for even light to resist, and thus it grows infinitely more impossible for anything slower to cross. The edge is not just distant, it is accelerating away faster than any traveler can pursue. It is as though the universe were conspiring to hide its vastness from us, giving us only a glimpse of its enormity before closing the curtain forever. This realization forces us into a sobering perspective. The cosmos we see is only a fleeting snapshot of a much larger reality, one we can never fully access. Dark energy guarantees that the story of exploration has an ending point, not because we will run out of determination, but because the laws of physics forbid us from continuing further. The true edge of the universe is not a boundary waiting to be reached, but a moving frontier pulled away from us at ever-increasing speed, ensuring that we will always remain in the center of a vanishing sphere of visibility. And yet, as disheartening as this may seem, it also compels us to treasure the present. We live at a unique time, when the universe is still legible, when galaxies across billions of light-years can still be seen, studied, and understood. We are cosmic witnesses standing at the threshold, aware of the vastness, but also aware of the limits. To appreciate just how unreachable this edge truly is, we must also consider the staggering scales of time and distance that separate human existence from the cosmic stage. A comparison that makes even our boldest explorations seem like whispers in eternity. When we talk about the impossibility of reaching the edge of the universe, one of the clearest ways to grasp it is by comparing human timescales with cosmic ones. Human beings live, on average, less than a century. Even civilizations themselves, in their recognizable forms, span only a few thousand years. Our entire technological history, from the first controlled fire to spaceflight, covers less than a blink in cosmic time. Yet the universe operates on scales of billions of years and distances so vast that even light, the fastest traveler known, needs billions of years to cross them. Against this backdrop, human lifespans and technological growth appear vanishingly small, as though we were fruit flies trying to comprehend the lifetime of a mountain. To put this into perspective, consider the nearest star beyond the Sun, Proxima Centauri, about 4.24 light-years away. With today's fastest spacecraft, such as the Parker Solar Probe or Voyager probes, it would take tens of thousands of years just to make that short interstellar hop. That is hundreds of times longer than all of recorded human history. Stretching further, our entire Milky Way galaxy spans about 100,000 light-years. Even at the speed of light itself, a speed we can never actually achieve, it would take 100,000 years to cross it from one side to the other. That's longer than Homo sapiens have existed as a species. And yet, the observable universe dwarfs the Milky Way so completely that it is like comparing a single grain of sand to all the beaches on Earth. Its diameter is about 93 billion light-years. Even in thought experiments where humans could travel at light speed, reaching the other side would take hundreds of times longer than the age of our species, and nearly 7 times the current age of the universe itself. Technology does not come close to bridging this gap. The Voyager 1 probe, launched in 1977, is the farthest human-made object, currently over 24 billion kilometers from Earth. That sounds like an enormous achievement, but it is only about 0.0025 light-years away, still inside our solar system's backyard, nowhere near even the closest star. If Voyager were aimed toward Proxima Centauri, it would take roughly 80,000 years to get there. And yet, Proxima Centauri is practically next door in cosmic terms. Imagine, then, the impossible chasm of distance separating us from galaxies billions of light-years away, slipping further from view every second due to cosmic expansion. Even with advances in propulsion technology, we remain bound by scales that make those destinations forever inaccessible. Another way to appreciate the disparity is to compare the timelines of human development with the universe's history. Our species has existed for roughly 300,000 years, and agriculture began only 12,000 years ago. In contrast, the universe has been around for 13.8 billion years. In that time, stars have lived and died, galaxies have collided and merged, and cosmic structures have evolved beyond our wildest imaginations. Yet human civilization has barely existed for the last blink of that cosmic eye. The idea that within such a short span we could hope to master journeys across billions of light-years is not just ambitious, it is fundamentally mismatched with the scales involved. Even if we imagine technologies advancing exponentially, the numbers remain crushing. Suppose we found a way to travel at 10% of the speed of light, an achievement requiring energy far beyond our current capabilities. At that speed, it would still take over 40 years to reach Proxima Centauri, meaning entire generations would pass before reaching even the closest destination. To cross our galaxy would still take 1 million years, and the observable universe would remain as unreachable as ever. Human biology is not designed to survive such timescales, nor is civilization stable enough to sustain projects that would last longer than recorded history itself. These scales also place an ironic twist on our desire for exploration. While the universe is unimaginably vast, our existence within it is fragile and short. On cosmic timescales, humanity itself may not even last long enough to attempt these journeys. Civilizations rise and fall in the span of thousands of years, while the universe continues expanding, galaxies receding, and cosmic structures evolving for billions more. The dream of reaching the edge is not just a problem of distance, but of time itself. We are temporary beings in a nearly eternal cosmos. This mismatch highlights the futility of imagining exploration on universal scales. Even our most optimistic visions, generation ships, suspended animation, or near light speed travel, fall apart when compared against the incomprehensible size and age of the cosmos. What we see in the night sky is not a destination we can ever reach, but a glimpse into a past so far removed from us that it feels almost like a separate reality. And if the passage of time will eventually lead to the universe's own decline, with energy spreading thin and stars extinguishing, then exploration has an ultimate deadline as well. The end of cosmic time itself will ensure that no edge is ever reached. To understand why, we must now look at the concept of heat death and how the universe may ultimately fade into darkness, leaving the question of an edge meaningless. When people speak of the ultimate fate of the universe, one of the most widely discussed scenarios is heat death, a haunting concept that stretches the imagination to its breaking point. It suggests not a fiery end, nor a sudden collapse, but an endless fading into silence and stillness. To understand why heat death would make the idea of reaching the edge of the universe impossible in principle, we must think not only in terms of distance, but in terms of energy, time, and the very laws of thermodynamics that govern everything from the burning of stars to the ticking of clocks. Heat death is not simply about the universe running out of fuel in the way a car engine runs dry. It is about the entire cosmos exhausting to do anything at all. At the heart of heat death lies the second law of thermodynamics, which states that in any closed system, entropy, the measure of disorder, always increases over time. On Earth, we notice entropy in the way ordered structures break down. Buildings decay, metals rust, heat spreads until it is uniform. The universe itself is the largest closed system we know, and it is subject to the same law. From the Big Bang onward, it has been running down, using up its free energy, the energy that can do work, and dispersing it more evenly across space. Stars burn their hydrogen into helium and heavier elements, releasing light and heat. Black holes devour matter and radiation. Galaxies collide, merge, and redistribute energy. But every one of these processes spreads energy more evenly, increasing entropy and reducing the gradients needed for work, motion, and complexity. Heat death is the state in which entropy has reached its maximum, when energy is so evenly distributed that no useful processes can occur anymore. In such a future, stars would no longer shine. Over trillions of years, they will exhaust their nuclear fuel, becoming white dwarfs, neutron stars, or black holes. White dwarfs will slowly cool into black dwarfs, cold, dead remnants radiating no heat or light. Black holes will persist longer, but even they are not eternal. Through a process called Hawking radiation, they will slowly evaporate over unimaginable timescales, eventually disappearing into nothingness. As all of this unfolds, the universe becomes colder, darker, and emptier. No engines can run, no stars can ignite, no new life can emerge. The cosmos approaches absolute zero in temperature, where energy differences vanish and motion ceases. It is the ultimate stillness, not because matter has disappeared, but because nothing meaningful can ever happen again. Now consider what this means for exploration. Reaching the edge of the universe was already impossible due to expansion and the speed of light. But heat death adds another layer of finality. Even if one imagined hypothetical civilizations lasting for trillions of years, with technologies so advanced they could cross galaxies, heat death would rob them of the energy required to keep going. Engines need fuel, and fuel requires usable energy gradients. When every corner of the universe has the same low energy state, there is nothing left to exploit. Ships cannot run, communication cannot occur, and even thought itself, which requires energy, becomes impossible. Exploration is not only physically cut off by the accelerating expansion of space, but cosmically silenced by the gradual exhaustion of energy itself. The edge becomes irrelevant because there is no longer any capacity to reach for it. The timescales involved in heat death are so vast that they make the lifetimes of stars seem like sparks. A typical star, like our Sun, lives for around 10 billion years. But heat death operates on timescales of trillions upon trillions of years. To put it in perspective, if the age of the universe today were written as a single second, then the journey to heat death would take longer than the entire recorded history of humanity multiplied countless times over. These numbers strain comprehension, yet they remind us that the cosmos, while seemingly eternal to us, is not infinite in its possibilities. It is slowly but inexorably sliding toward a state in which edges, horizons, and destinations no longer matter. For humanity, the vision of heat death highlights the fragility of our place in the cosmos. Even if we survived extinction events on Earth, even if we colonized our galaxy, even if we found ways to endure billions of years, the universe itself is on a trajectory toward lifelessness. There will come a time when galaxies no longer sparkle in the night, when no telescopes can detect the glow of stars, when no traveler can hope to cross the gulfs of space because the gulfs will be nothing but empty, cold void. The final silence of the universe ensures that exploration as we know it, driven by curiosity, fueled by energy, and sustained by light, must one day end. Yet heat death also confronts us with a deeper truth. Perhaps the idea of reaching the edge was always symbolic rather than literal. The edge of the universe is not a physical boundary we could ever touch, but a metaphor for the limits of our knowledge and power. In a cosmos doomed to fade into heat death, chasing the edge is like chasing the horizon across a desert that only grows larger and emptier the further you walk. It cannot be reached because it is not there in the way we imagine it. Heat death strips away the illusion that perseverance alone could ever bring us to the ultimate frontier. Still, there is something oddly poetic in this bleak picture. The same laws that guarantee the death of stars also made possible their birth. The same entropy that guarantees eventual stillness also gave rise to complexity, life, and the brief window of consciousness through which we can ask these questions. Our longing to reach the edge of the universe will never be fulfilled, not because our ambition is too small, but because the universe itself is too vast and bound by unyielding rules. And as we reflect on heat death, we are drawn naturally to another realization. Perhaps we are wrong to think of an edge at all. Perhaps the universe has no boundary in the first place, but instead curves back on itself in ways we struggle to imagine. When we speak about the edge of the universe, we do so by borrowing language from our everyday experiences. Edges, borders, and boundaries are familiar to us in the physical world. We encounter the edge of a cliff, the shoreline of an ocean, or the walls of a room. These are tangible, finite borders where one thing ends and another begins. But the universe resists this kind of thinking. What seems like an intuitive question, where does the universe end, may in fact have no answer, because there may be no edge at all. Instead, the cosmos could be boundless yet finite, curved in a way that closes on itself, like the surface of a sphere. This is the illusion of an edge, the idea that while our minds crave a boundary, the universe may simply go on without one. To visualize this, think about Earth. If you stand on a flat plain, the land stretches to the horizon and it feels endless. But we know Earth is finite, a sphere with no edges. You could travel around the planet indefinitely, always moving forward, never encountering a wall or a stopping point. The boundary exists in terms of geometry, not in the form of a physical edge. Many cosmologists believe the universe could be similar, finite in size, yet unbounded, curving in higher dimensional space so that if you traveled far enough in one direction, you might eventually return to your starting point. In such a model, the edge is a misunderstanding born of trying to apply linear thinking to something fundamentally non-linear. Of course, it is also possible that the universe is infinite stretching endlessly in all directions without repetition. In that case, the search for an edge becomes even more meaningless. Infinity has no boundaries. No matter how far you travel, there will always be more beyond. For human imagination, infinity is profoundly unsettling, because we are accustomed to finite things. Yet in physics and mathematics, infinity is a legitimate possibility, and current observations suggest that the universe may indeed be infinite or so vast that it is indistinguishable from infinity to us. If this is true, then asking about an edge is like asking where a number line ends. It doesn't. This idea challenges the very framework of exploration. If there is no edge, then there is no ultimate destination to reach. Our explorations become journeys into depth rather than toward an endpoint, probing deeper into the nature of matter, energy, and space-time itself, rather than imagining a final wall where it all stops. The concept of an edge is appealing because it gives us a goal, but the absence of one is far more humbling. It suggests that the universe is not a container we can map in its entirety, but a vast, possibly infinite continuum in which we can only ever experience a fragment. Cosmic expansion further reinforces this illusion of an edge. As the universe grows, it doesn't expand into something else. There is no outer void beyond the cosmos that space is spilling into. Expansion means that distances between objects increase, not that space is filling up an external container. This is counterintuitive because we are used to balloons inflating into the air around them. But the universe has no external environment in which to expand. It simply stretches itself without needing an outside backdrop. This means there is no edge because there is no outside. The universe is everything there is, and by definition, everything cannot have a boundary in the way objects within it do. The illusion of an edge also has a psychological dimension. Human beings evolved in finite environments, forests, valleys, continents. We instinctively expect limits and borders because those shaped survival. But at cosmic scales, our instincts betray us. We imagine a wall or a cliff at the end of space because that fits our sense of boundaries. In truth, space may be far stranger, endless, curved, or multidimensional. The very question of an edge may reveal more about the limits of human perception than about the structure of reality. This perspective reframes the impossibility of reaching the edge of the universe. It is not only that physical laws and cosmic expansion prevent us from ever getting there. It may be that there is nothing to get to in the first place. Chasing the edge might be like chasing the horizon on Earth. No matter how far you travel, the horizon always moves farther away because it is not a physical object, but a perspective created by your position. In the same way, the cosmic edge may exist only in our imaginations, a product of trying to impose finite concepts on an infinite or curved reality. And yet, just as the illusion of an edge inspires questions, it also leads us to deeper mysteries. If the universe has no edge, does it mean it is all there is? Or could it be only one of countless universes, each with its own properties, boundaries, or lack thereof? The possibility of a multiverse introduces an even stranger kind of edge, not one within our universe, but one that marks the limits of our universe compared to others. And if such universes exist, they may forever remain beyond our reach, sealed away by barriers of physics more insurmountable than even the speed of light. The multiverse is one of the most daring and unsettling ideas to emerge from modern physics, a concept that suggests our universe, the galaxies, stars, planets, and even the very laws of physics we know, may be only one bubble in an unimaginably vast cosmic sea. If true, it reframes the question of an edge entirely. Instead of asking where our universe ends, we must ask whether it is embedded within something larger. a grander reality where multiple universes coexist, each perhaps governed by its own set of rules. But even if such a multiverse exists, the crucial truth remains: we will never reach it. The boundaries separating universes are not like the borders between the voids between galaxies. They are fundamental divides in the very fabric of existence, unbridgeable in principle. There are several hypotheses that point toward a multiverse. One comes from inflationary cosmology, which proposes that the rapid expansion of the early universe did not happen everywhere in the same way. Instead, inflation may have occurred in patches, creating separate bubbles of space-time. Our universe would then be one bubble among many, each one forming its own universe with possibly different physical constants. In this scenario, inflation never truly ends. It continues eternally in some regions, spawning new universes endlessly in a process called eternal inflation. Each bubble expands into its own cosmos, isolated forever from its neighbors by regions of space still undergoing inflation faster than light can cross. The edge of our universe, in this picture, is not an edge we could ever approach, but a horizon of inflation that prevents contact with anything beyond. Another hint comes from quantum mechanics. In the many worlds interpretation, every quantum event does not collapse into a single outcome, but branches into multiple realities. Each possibility plays out in its own universe, splitting reality into countless versions. In one universe, a star explodes. In another, it does not. In one, life evolves on Earth. In another, it fails to. These universes occupy no physical space that we can reach. They are parallel realities, coexisting with ours in ways we cannot touch. If true, then the edge of our universe is not a wall, but a limit of perception. We inhabit one branch of reality, while infinite others continue beyond our awareness, forever inaccessible. String theory offers yet another possibility. In some versions, the fundamental building blocks of the universe are not particles, but tiny vibrating strings, and the mathematics suggests that many more dimensions may exist beyond the familiar 3 of space and 1 of time. These extra dimensions could house entirely separate universes, sometimes referred to as brains. Our universe would then be a 4-dimensional brain floating in a higher dimensional space, alongside others that we can never contact. Collisions between brains might even explain cosmic events like the Big Bang. But unless we find a way to step into higher dimensions, which so far appears impossible, these neighboring universes remain forever hidden from us, as unreachable as dreams. The philosophical implications of the multiverse are staggering. If there are countless universes, then the edge of our universe is not the ultimate frontier, but merely the edge of one domain among many. But because of the insurmountable barriers, expansion, dimensional divides, or quantum isolation, we could never cross from one to another. The multiverse may exist all around us, yet we are permanently confined to our cosmic bubble, unable to confirm or explore what lies beyond. The very idea stretches the limits of science because it blurs the line between what is testable and what is speculation. Observational cosmology can only tell us about our observable universe. Everything beyond is, by definition, beyond the reach of light, signals, or experiments. For human exploration, this is the ultimate humbling perspective. Even if we mastered the ability to travel at light speed, even if we somehow overcame expansion itself, the edge of our universe would still not deliver us into another. The boundaries between universes, if they exist, are not physical distances we can cross, but barriers of physics itself. They are absolute separations that define realities apart from one another. To imagine reaching the edge of the universe in hopes of finding another is like expecting to walk to the end of a rainbow. No matter how far you travel, the goal always recedes, because it is not a destination that exists in the way you imagine. And yet, the multiverse concept also magnifies the wonder of existence. If we are trapped in one bubble among countless others, then the very fact that we exist here in a universe that allows stars, planets, and life is astonishing. It means that in an endless sea of possibilities, this particular cosmos happens to support beings capable of questioning its edges. While the multiverse may forever remain beyond our reach, its possibility deepens the meaning of our search, showing us that the edge of the universe is not merely a question of travel, but of understanding existence itself. From here, the question naturally turns to what it would actually take, in terms of energy, to attempt such impossible journeys. Even if we ignore multiverse barriers and focus only on reaching the edge of our own observable cosmos, the energy requirements alone make the dream collapse under its own weight. When we imagine traveling to the edge of the universe, even if we set aside the cosmic expansion and the unreachable horizons, we quickly run into another inescapable reality: energy. Moving through space is never free. Every acceleration, every attempt to push against gravity, every effort to maintain life in the cold void requires energy. And when the distances are measured not in kilometers but in billions of light years, the energy demands climb to levels that make even our most ambitious technologies look trivial. Exploring this problem exposes the sheer absurdity of the dream. It is not merely improbable, but so far beyond our capability that it strains imagination. Let's start with something familiar: sending a spacecraft beyond our solar system. Voyager 1, launched in 1977, is the farthest human-made object from Earth. To achieve this, it used rocket fuel combined with gravitational slingshots around planets to gather momentum. Yet despite decades of travel, it has only moved a fraction of a light year. To reach the nearest star, Proxima Centauri, it would need around 80,000 years, and that is just 4 light years away. The observable universe stretches nearly 93 billion light years in diameter. Even at our most optimistic, the difference is staggering. If Earth's fastest spacecraft today is like a person crawling across a room, traveling to the edge of the universe would be like trying to walk across every desert, ocean, and mountain on the planet. Not once, but trillions upon trillions of times over. Now, suppose we set a loftier goal, achieving speeds close to the speed of light. Physics allows us to calculate the energy requirements, and the results are sobering. The kinetic energy of an object increases dramatically as it approaches light speed, following the rules of Einstein's relativity. At half the speed of light, the energy needed is already immense, equivalent to the total energy output of entire nations for years. At 90% of the speed of light, the energy requirements grow exponentially. To accelerate something the size of a modest spacecraft carrying humans to even 99% of light speed would require energy on the order of what stars release. And to push it closer still, to 99.999% of light speed, the energy requirement climbs toward infinity. That means no amount of fuel, no amount of solar power, no clever engineering trick could ever make it possible. The laws of physics themselves demand more energy than the universe can provide. Even theoretical propulsion concepts quickly run into this wall. Nuclear fusion drives, antimatter engines, and even harnessing black holes have been proposed as ways to power near light speed travel. Antimatter, in particular, is attractive because it converts mass into energy with 100% efficiency. But here's the catch. To create even a few grams of antimatter requires enormous energy input, far more than the energy it can return. Producing enough antimatter to power a starship for intergalactic travel would require energy equivalent to the total output of our Sun for years or longer. It is an energy budget humanity could never afford. And even if we somehow harvested entire stars for fuel, cosmic distances would still demand more energy than we could extract before the universe itself aged into darkness. Energy limitations don't stop at propulsion. Keeping humans alive on such journeys would also be unimaginably expensive. Every breath of air, every drop of water, every bite of food requires energy to produce, recycle, and maintain. On a voyage lasting millions of years, life support would demand staggering amounts of energy. Energy that would not only need to be stored, but also shielded from the hostile radiation of deep space. In practice, maintaining life for even a few centuries of travel is beyond our ability. Extending that to the timescales required to chase the edge of the cosmos is inconceivable. Even if we stripped away life support and imagined robotic probes instead, the challenge doesn't shrink much. Machines also require power, shielding, and redundancy to survive cosmic radiation and micrometeoroid impacts. To push such probes across billions of light-years would require unimaginable amounts of energy, far beyond the cumulative output of all the civilizations that could ever exist on Earth. The energy wall makes clear that the barrier is not just about distance, it is about feasibility. The price of reaching the edge is a currency the universe never minted enough of. The irony is that even as we contemplate these vast energy demands, the universe itself provides examples of raw power on inconceivable scales. Supernovae unleash more energy in a few seconds than our Sun will release in its entire lifetime. Black holes swallow stars whole, releasing torrents of energy in the process. And yet, even these colossal engines cannot move matter across the gulfs of the cosmos. Nature itself, with all its raw power, does not appear to offer a solution. If stars and galaxies cannot overcome these scales, neither can we. Energy limitations are therefore not just practical hurdles, but fundamental impossibilities. They underline why the edge of the universe will never be a destination. No matter how much energy we gather, no matter how efficient we become, the demands of relativistic travel outpace our capacity. And this realization points us toward an even deeper problem. Even if we could find ways to generate or harness cosmic amounts of energy, we would still run headlong into the ultimate barriers of physics themselves. Technology, no matter how advanced, cannot rewrite the laws of space-time. The very concepts of warp drives, wormholes, and shortcuts through the cosmos all flirt with ideas that appear to break the rules of reality. It is here that we see not only energy constraints, but also technological barriers that lock the universe's edge away from us forever. When the conversation turns to reaching the edge of the universe, people often look to futuristic technologies as potential saviors. If rockets and probes are too slow, maybe there are clever workarounds hidden in the equations of physics, warp drives, wormholes, or hyperspace shortcuts that allow us to bend the rules of travel. These ideas are endlessly popular in science fiction, and for good reason. They offer hope that we might sidestep the crushing scales of energy and distance that confine us. Yet when examined through the lens of real physics, they reveal insurmountable barriers. They are not merely impractical with current technology. They appear to require conditions that reality itself may not allow. The dream collapses not on the launch pad, but in the math. Take the concept of a warp drive, popularized by science fiction but seriously considered in theoretical physics through models like the Alcubierre drive. The idea is simple, yet audacious. Instead of moving a ship through space faster than light, you compress space in front of the ship and expand it behind, carrying the vessel along on a wave of space-time itself. This sidesteps the cosmic speed limit because the ship never technically moves faster than light. It is space that moves around it. But to achieve such a feat, the equations demand something that does not exist in the natural world: negative energy density or exotic matter. This is not just rare, it may be impossible. Even if it could exist, the amount required would be astronomical, equivalent to the mass energy of entire stars or even universes. Worse, such a drive would create paradoxes in causality, potentially allowing time travel and violating the very consistency of space-time. The warp drive remains a tantalizing thought experiment, but one that shatters against the limits of known physics. Wormholes present another tempting shortcut. In theory, wormholes are bridges that connect two distant points in space-time, folding the fabric so that a journey of billions of light-years could be replaced with a single step. General relativity does allow wormholes in its equations, but reality is not so accommodating. First, wormholes would collapse instantly unless held open by the same kind of exotic matter that warp drives require. Second, even if they could remain stable, creating or finding one large enough for travel would demand manipulating gravitational forces comparable to those near black holes, regions where physics as we know it breaks down. Third, wormholes, if they exist at all, would be plagued with problems of instability, radiation buildup, and causality violations that render them unusable. They are mathematical curiosities, not engineering blueprints. Even less exotic proposals, like generation ships or suspended animation, falter under scrutiny. Generation ships imagine vast habitats where thousands of people live and die across centuries or millennia, slowly moving toward distant stars. But even if we solved the staggering social, biological, and engineering challenges of maintaining such vessels, they would still move at a crawl compared to cosmic scales. They might reach nearby stars after thousands of years, but never cross galaxies, much less the observable universe. Suspended animation, or digital consciousness, faces the same scale problem. Freezing time for travelers does not shrink the distances. The ship would still need fuel, shielding, and energy across journeys that outlast not only civilizations, but perhaps entire epochs of cosmic history. The barriers extend even to more speculative technologies. Concepts like harvesting energy from black holes, building Dyson spheres around stars, or tapping into zero-point energy have all been proposed as ways to unlock nearly limitless power. Yet none of these solve the deeper issue. Space-time itself sets rules that no amount of power can overturn. You can collect all the energy you want, but you cannot use it to surpass the speed of light or to stabilize wormholes that reality refuses to allow. Technology is bounded not just by imagination, but by the immutable structure of the cosmos. What makes these barriers so profound is that they are not failures of creativity. They are failures imposed by the very equations that describe reality. Physics is not a puzzle waiting for us to find the right key. It is a framework that defines what is possible. Warp drives, wormholes, hyperspace, all of these ideas push against the boundaries of that framework, and so far, the framework has not budged. Every attempt to twist it results in paradoxes, infinities, or demands for materials and energies that do not, and perhaps cannot exist. The universe is not being stingy, it is being consistent. This is why technological optimism alone cannot overcome the impossibility of reaching the edge of the universe. We are not merely short on resources or cleverness. We are bound by the laws of space-time itself. The dream of slipping across the cosmos in an instant belongs to fiction, not physics. And yet, even if we somehow accepted slower than light travel as our only option, we would still run into another fundamental barrier: time itself. Relativity offers strange effects like time dilation, which can make long journeys seem shorter for travelers, but this does not erase the cosmic scales that lie ahead. it is to these relativistic effects and their ultimate inability to solve the problem that we must now turn. Time dilation is one of the strangest and most fascinating predictions of Einstein's theory of relativity. It tells us that time does not flow the same way for everyone in the universe. It depends on how fast you are moving and how strong the gravitational field around you is. The faster you travel, especially as you approach the speed of light, the slower time passes for you relative to those who remain behind. This effect is not just theoretical. It has been measured in particle accelerators, where subatomic particles moving close to light speed live longer than they should, and even in astronauts whose clocks tick ever so slightly differently than those on Earth. At first glance, time dilation seems like a possible loophole to the cosmic speed limit. If time slows down for travelers, maybe long interstellar or even intergalactic journeys could be completed within a single lifetime, even if they take millions of years from the perspective of the universe. But the cruel truth is that while time dilation eases the burden for the traveler, it does not erase the immensity of cosmic distances, nor the expansion of space that places most of the universe permanently out of reach. To illustrate, imagine a spacecraft accelerating to 99.9% of the speed of light. For its passengers, the effects of time dilation would be dramatic. A journey that might take thousands or even millions of years as measured on Earth could feel like only a few decades aboard the ship. From the perspective of the crew, they could cross vast regions of space and still experience the passage of time within the span of a human life. But from the perspective of everyone left behind on Earth, entire epochs would pass. Civilizations would rise and fall, stars would be born and die, galaxies would collide, and the universe itself would evolve while the crew remained locked in their relativistic bubble. This mismatch of timelines creates a paradoxical sense of progress. The travelers could outrun the universe's clock, but not the physical distances that continue to expand ahead of them. Even in this optimistic scenario, the limits remain crushing. To cross the observable universe, which stretches about 93 billion light-years across, would still take far longer than the universe has even existed. Time dilation may allow travelers to personally experience shorter journeys, but it cannot shrink the actual distance. Moreover, the closer one gets to light speed, the more energy is required to maintain it, an amount that quickly becomes impossible to generate. Even if energy were no issue, the passengers would find that their destination galaxies are receding faster than they can ever reach. The expansion of space means that no matter how much relativity bends their perception of time, the horizon of unreachable regions grows faster than they can chase it. Another complication is survival. Time dilation makes long journeys feel shorter for travelers, but it does not freeze the effects of deep space. Radiation exposure, collisions with even tiny particles at near-light speeds, and the need for life support over subjective decades remain real. A ship moving near the speed of light would be constantly bombarded by interstellar dust and gas, each particle slamming into the vessel with energies comparable to nuclear explosions. Shielding against this requires impossible levels of protection, which again translates to impossible amounts of energy. Relativity may bend time, but it does not bend the laws of engineering or biology. There is also the emotional and philosophical cost. A traveler could leave Earth, journey across galaxies within what feels like a lifetime, and return to find that billions of years have passed. Humanity may be long gone, Earth itself unrecognizable, the sun extinguished, and galaxies vanished over the horizon of expansion. In a sense, time dilation offers a way to escape the confines of human lifespan, but at the cost of severing all ties to the universe we know. It replaces one impossibility, the sheer length of cosmic journeys, with another, the impossibility of staying connected to the world from which we depart. Thus, Time dilation is not a solution to the problem of reaching the edge of the universe. It is at best a trick of perception, allowing travelers to bypass their own mortality while leaving the fundamental barriers untouched. The distances remain vast, the energy requirements remain infinite, and the expansion of space continues to outrun even the fastest ships. Time dilation makes the journey survivable in theory, but not achievable in practice. The universe is simply too large, too dynamic, and too unforgiving for relativity to save us. And beyond this relativistic problem lies another sobering truth. Even without traveling, the universe itself is slowly slipping away from us. Galaxies are receding, their light stretching until it vanishes into invisibility. The cosmos is fading, and in the future, much of what we see today will disappear from view forever. To understand why the dream of reaching the edge becomes more hopeless with each passing moment, we must now turn to this vanishing act, the fading universe itself. One of the most haunting realities of modern cosmology is that the universe we see today is not the universe future observers will inherit. The cosmos is fading, not because the stars are dimming, though eventually they will, but because the expansion of space itself is stretching light from distant galaxies until it slips beyond visibility. This process is known as redshift. As galaxies recede from us, the light they emit is stretched to longer wavelengths, shifting from visible light into infrared and eventually into radio waves so faint that no telescope could ever detect them. What this means is that the night sky, as vast and filled with galaxies as it appears to us today, is only temporary. Slowly, inevitably, the distant cosmos is disappearing, pixel by pixel, into an unreachable darkness. We already observe this effect in action. Galaxies farther away from us are more redshifted than those nearby, a direct consequence of the expanding universe. This is not motion in the usual sense. Galaxies are not speeding through space like cars on a highway. Instead, the space between us and them is stretching, carrying them away in every direction. The more distant a galaxy, the faster it recedes, and the more its light is redshifted. Eventually, at extreme distances, galaxies move away faster than light itself because of cosmic expansion, and the light they emit can never catch up to us. Those galaxies are effectively erased from the observable universe. Their stars may shine for billions of years, but their light will never reach us again. This process is accelerating because of dark energy, which is pushing galaxies away at an ever faster pace. In the far future, hundreds of billions of years from now, only the closest galaxies, those gravitationally bound to the Milky Way, such as Andromeda and the members of our local group, will remain visible. Everything else will have redshifted out of view. For astronomers living in that distant epoch, the universe will appear empty and static, with no evidence of the cosmic web of galaxies and clusters we observe today. They would see only a small island of stars surrounded by infinite blackness, unaware that a grander universe ever existed. In this sense, our time is privileged. We live in a cosmic window where the vastness of the universe is still on display before the curtain of redshift falls. The fading universe is not just an observational tragedy. It is another barrier against the dream of reaching the edge. Even if we could one day build technologies capable of intergalactic travel, many of the destinations we see today would vanish before we could ever reach them. Their light will stretch into invisibility long before we cover even the tiniest fraction of the distance. Worse, their physical separation from us grows faster than light speed, ensuring they slip not only out of view, but out of existence from our perspective entirely. In a very real sense, the universe is actively erasing the map of possible journeys as time goes on. This disappearance, also reshapes how we think about the concept of the edge. The observable universe is defined by what light has had time to reach us since the Big Bang. But as expansion accelerates, that observable boundary becomes less meaningful. The galaxies beyond are not just hidden, they are cut off forever, lost behind horizons that no ship or signal could ever cross. The edge is not static, like the edge of a table. It is dynamic, retreating, and selective. Every moment, more galaxies pass across it, gone forever. The cosmos is not infinite in what it reveals, but finite and shrinking in the stories it tells us. From a philosophical perspective, this fading cosmos deepens the poignancy of human existence. We live at a moment when the night sky still reveals the past, when light from galaxies billions of years old still streams toward us. We can study cosmic history, trace the formation of galaxies, and glimpse the afterglow of the Big Bang itself. But future beings will not have this privilege. For them, the evidence of cosmic origins will be gone. They may never know of dark energy, of cosmic expansion, or of the galaxies that once filled the universe. Their cosmos will seem small and eternal, when in fact it is neither. In that way, our time is uniquely blessed with a cosmic horizon still alive with light. And yet, for all our privilege, the fading universe underlines the futility of chasing the edge. No matter how advanced our technology becomes, the frontier retreats faster than we can follow. We are not explorers standing at the base of a mountain we have yet to climb. We are children at the shoreline, watching the sea itself withdraw into the distance, carrying the horizon away with it forever. The fading of galaxies is not just a visual loss, but a profound reminder that the universe does not wait for us. Its expansion, its redshift, its erasure of the distant past proceed regardless of our dreams. This cosmic vanishing act brings us back to a sobering truth. Even if light itself cannot bridge these distances, neither can we. The fading of the universe is the ultimate proof that the edge will never be a place we can reach. But even before the stars vanish from our sight, another barrier stands in our way: the limits of our own biology and survival. For even if physics allowed such journeys, the human body and mind may not. The dream of cosmic exploration runs aground not only on the rules of the universe, but also on the frailty of the travelers themselves. Human ambition has always outpaced human endurance. We have crossed oceans, climbed mountains, and touched the moon, not because our bodies were built for such feats, but because we devised tools to overcome our limitations. Yet when it comes to the dream of reaching the edge of the universe, biology itself becomes one of the most unforgiving barriers. Even if we solved every engineering problem of propulsion, even if we bent time with relativity or built vast generation ships, we would still face the fundamental fragility of human life. Our bodies are tuned to Earth's gentle gravity, our atmosphere's protective shield, and a narrow range of conditions. Remove us from that cradle for long enough, and the limitations of flesh and biology make themselves brutally clear. The first challenge is time. Human lifespans are short compared to cosmic journeys. Even at the speed of light, utterly unattainable in practice, it would take tens of thousands of years to cross our galaxy and billions of years to approach the edge of the observable universe. No human body could survive such spans, even with advanced medicine. The idea of generation ships, where entire populations live and die aboard vast vessels, transferring the mission across centuries, highlights the issue. Maintaining health, genetic diversity, psychological stability, and social cohesion over such spans is not merely difficult, it verges on impossible. Civilizations on Earth collapse within thousands of years, often sooner. Expecting one to thrive in isolation for hundreds of millennia in deep space is a gamble against history itself. Radiation is another lethal obstacle. Beyond Earth's atmosphere and magnetic field, space is filled with high-energy cosmic rays and solar particles. Over decades, this radiation damages DNA and compromises organ systems. Shielding against it requires massive protective layers, which increase spacecraft mass and therefore the energy needed to move it. Even then, no shielding is perfect. Over centuries or millennia, exposure would accumulate to deadly levels. A ship crossing interstellar space at near light speeds would face an even more devastating hazard: collisions with dust particles. At such speeds, even a grain of sand striking the hull would release energy comparable to a bomb. Protecting against countless impacts across light years is not a solvable engineering issue. It is a fundamental limit of physics and survival. Then comes the problem of resources. Humans require a continuous supply of oxygen, water, and food, all of which must be recycled on long voyages. On Earth, our biosphere performs this balancing act effortlessly, powered by sunlight and ecosystems that took billions of years to evolve. In space, we would need closed-loop life support systems, artificial ecosystems with no waste, no breakdowns, and no margin for error. Experiments on Earth, such as Biosphere 2, have shown how fragile such systems are. They fail easily, collapsing under imbalances in oxygen, carbon dioxide, or microbial populations. Now scale that problem to a ship traveling for thousands or millions of years, cut off from resupply, where one failure means extinction. The fragility of life support systems makes survival across cosmic spans almost impossible. Psychology may be the most underestimated barrier of all. Humans are social and emotional beings, not machines. Extended isolation, confinement, and separation from Earth's rhythms can erode mental health even in short-term missions. Astronauts aboard the International Space Station already report stress, anxiety, and interpersonal tensions despite rigorous training and short durations. Now imagine countless generations growing up aboard a ship, never seeing Earth, never feeling gravity or fresh air, never knowing a sunrise or a horizon. The weight of monotony, the loss of cultural continuity, and the breakdown of shared purpose could unravel any long-term mission. A voyage lasting millennia is not just a technical challenge, but a psychological one. Humanity may not be wired to withstand. Even if we imagine solutions, genetic engineering to strengthen bodies against radiation, artificial intelligence to stabilize societies, cryogenic sleep to skip centuries, none of these overcome the ultimate barrier: time and entropy. Biological systems degrade. DNA accumulates mutations. Machines break down. Materials weaken under radiation and cosmic dust bombardment. Even the best engineered systems have lifespans, and the longer the journey, the greater the probability of failure. The universe itself becomes the enemy, wearing down the travelers bit by bit until survival becomes impossible. In this way, human survival limits echo the larger truths of physics. The cosmos is simply too vast, too hostile, and too enduring for fragile biological beings to conquer. Our ambition to reach the edge collides with the reality that our bodies and minds are designed for short lives on a single planet, not endless odysseys across galaxies. The edge of the universe is not simply unreachable because of light speed or expansion, but because the travelers themselves could never endure the journey. And this leads to a deeper, more philosophical question. If survival and physics both forbid us from ever reaching the edge, then what do we even mean when we ask about the edge at all? Perhaps the very concept is a misunderstanding, a projection of human instincts onto a cosmos that has no border to begin with. When we ask whether humans will ever reach the edge of the universe, we may be exposing more about the way we think than about the cosmos itself. The very idea of an edge comes from human experience. We know the edges of rivers, the ends of roads, the rim of the Earth's continents, and the walls that enclose our cities. We live in a finite world filled with boundaries, so we instinctively project this structure onto the universe. But what if the universe does not have an edge in the way our imagination insists? What if the edge is not a physical border at all, but simply the limit of what we can observe? A horizon carved not into the universe, but into our own perception. The observable universe gives us a clue. It forms a sphere around us about 46 billion light-years in radius, not because the universe ends there, but because that is as far as light has had time to travel since the Big Bang. Beyond that horizon, there may be more galaxies, more cosmic structures, perhaps even radically different regions of space, but they are forever invisible to us. This raises the philosophical possibility that the edge is not something out there, waiting to be reached, but something inside us, a consequence of our position in time and space, of being creatures who measure reality through light and causality. The edge is the boundary of knowledge, not the boundary of existence. This interpretation reframes exploration entirely. Instead of picturing a spaceship hurtling toward a wall at the universe's farthest boundary, we realize that the edge is wherever our instruments stop working, wherever light fails to reach us. It is dynamic, not fixed, receding as the universe expands and as technology pushes our observational capabilities further. Each new telescope, each new detector extends our edge a little farther, but the process is endless. No matter how advanced we become, there will always be a new horizon, a new boundary of ignorance just beyond reach. In this sense, the edge is not a destination, but a moving frontier, forever inspiring curiosity while forever denying conquest. This raises a deeper philosophical question. If the edge is only an artifact of observation, does it exist at all? A horizon is not a thing in itself. It is an illusion of perspective. When we stand on a plane and see the horizon line, it feels like the land ends there. But as we walk forward, the horizon retreats. There is no actual line on the ground. It is an artifact of where we stand. The same may be true of the universe. What we call the edge may be nothing more than a cosmic horizon, a mirage created by the finite speed of light and the finite age of time. The mistake lies in treating this illusion as if it were a wall that could be reached. There is also a sobering humility in this view. For centuries, humanity has imagined itself as explorers destined to conquer all frontiers. We have crossed seas, charted continents, and ventured into space. But the philosophical lesson of the edge of the universe is that not all frontiers are conquerable. Some are illusions, limits not of courage or willpower, but of reality itself. The edge, in this sense, is not a place we can journey to, but a mirror reflecting back the boundaries of human perception and understanding. To speak of reaching it is to misunderstand what it is. And yet, this does not diminish the value of the question. On the contrary, it makes it more profound. Asking about the edge of the universe forces us to confront what it means to know anything at all. Are we limited to the observable? Does the unobservable count as real if it can never interact with us? Is the universe only what we can measure, or does it extend infinitely beyond our comprehension? These are not merely scientific questions, but philosophical ones, blurring the line between physics and metaphysics. The edge is where science touches mystery, where equations meet the limits of thought. Seen this way, the edge is less about a boundary in space and more about a boundary in meaning. It is the horizon between knowledge and ignorance, between what we can verify and what we can only imagine. We may never reach it because it is not a thing to be reached. It is a question, an invitation, a challenge. The universe has given us a mirage to chase, not to catch. And in chasing it, we learn more about ourselves than about the cosmos. From this philosophical vantage point, the question naturally shifts. Instead of asking whether we can reach the edge, we must ask how our small human lives and ambitions fit against the backdrop of such incomprehensible scales. The mismatch between the cosmic and the human becomes impossible to ignore, reminding us that our yearning to reach the edge may say more about our need for meaning than about the structure of the universe. The universe is a theatre of scales so vast that human imagination collapses under its weight. When we talk about travelling to the edge, we reveal the profound mismatch between human ambition and cosmic reality. Our species evolved on a small rocky planet, where distances were measured in steps, journeys in days, and lifetimes in decades. For most of history, the farthest a person could dream of travelling was across mountains or seas. Now, in the age of space exploration, we speak casually of stars, galaxies, and universes. But our bodies, our lifespans, and our technologies remain the same fragile tools of a planetary species. The cosmos dwarfs us, not just in size, but in every dimension of time, distance, and endurance. Consider the simple comparison between Earth and the universe. Earth's circumference is about 40,000 kilometers. The Moon, our closest celestial neighbor, lies 384,000 kilometers away. Mars, the next great frontier, is tens of millions of kilometers away, depending on orbital alignment. Already, reaching Mars poses immense challenges: years of travel, hazardous radiation, the need for enormous resources. And yet, the nearest star system, Proxima Centauri, lies 40 trillion kilometers away. That's a jump in scale so enormous it defies intuitive grasp. It's like comparing the length of a football field to the distance from Earth to the Sun. And Proxima Centauri is practically next door compared to the rest of the galaxy. The Milky Way itself is 100,000 light-years wide, containing hundreds of billions of stars. Even if we could travel at 1/10 the speed of light, a feat that is far beyond our current capabilities, it would take 1,000,000 years to cross it. And beyond our galaxy lie trillions more, spread across a cosmic web that extends for tens of billions of light-years. Each step up in scale multiplies the challenge beyond reason. By the time we speak of reaching the edge of the observable universe, we are not even in the realm of practical impossibility. We are confronting something so beyond human proportions that it belongs to the category of paradox. Human goals are shaped by human timescales. We think in decades and centuries at most. Civilizations rise and fall in spans shorter than the time it would take to reach even the nearest stars. Our technologies evolve rapidly, but they do so within the context of societies that themselves are fragile and impermanent. Cosmic exploration, by contrast, demands stability across millions or billions of years. It asks of us patience and persistence far beyond anything human history has ever demonstrated. The mismatch is not simply one of distance, but of endurance. The universe operates on timescales that make human determination irrelevant. This disparity forces us to confront an uncomfortable truth. The universe is not built to be traversed by creatures like us. It is not a playground, not a destination to be crossed. It is a vast, indifferent expanse where our notions of edges and goals are almost laughably small. From the perspective of the cosmos, even the greatest human achievements, landing on the moon, sending probes to the outer planets, glimpsing the faint afterglow of the Big Bang, are tiny sparks, flickers of light in an ocean that stretches forever. To imagine reaching its farthest limits is to forget how fragile those sparks are. And yet, there is also beauty in this mismatch. The very fact that small beings on a pale blue dot can even ask about the edge of the universe is extraordinary. We may never match the universe in scale, but we match it in curiosity. Our exploration goals may be minuscule compared to the cosmos, but they carry meaning precisely because of that contrast. To look up at the night sky and ask about its boundaries is to step beyond our limitations in thought, even if not in travel. The mismatch reminds us not of our weakness, but of the miracle that we can even think in such terms at all. Still, the paradox remains. We yearn to reach the edge of something that may not exist, while the cosmos ensures that even if it did, it would always recede faster than we could follow. This paradox is the final twist in the story, showing us that the dream of reaching the edge is not only impossible, but logically self-defeating. The universe itself ensures that the more we chase, the farther the edge runs away. The dream of reaching the edge of the universe has a built-in contradiction, a paradox that exposes the limits of both human imagination and the very structure of reality. At its core, the paradox is this: even if we had infinite time, infinite endurance, and technologies so advanced they could erase every practical obstacle of distance, energy, and survival, the edge of the universe would still remain forever out of reach. This is not merely because of the scale of the cosmos or the speed of light. It is because of the way the universe itself expands. The edge is not a fixed location waiting to be discovered. It is a moving frontier, receding faster than any traveler could ever chase. To pursue it is to chase a horizon that will always remain ahead, no matter how far we go. The paradox begins with the difference between movement through space and the expansion of space itself. When we imagine traveling to the universe's edge, we often picture it as a journey across terrain, like walking across a continent or flying across an ocean. But space does not work like that. Galaxies are not flying through a static void. Rather, the void itself, the very fabric of space-time, is stretching. This means that while no object can move through space faster than light, the space between objects can expand faster than light, carrying galaxies away at speeds that defy pursuit. The farther away a galaxy is, the faster it recedes, and beyond a certain point, it recedes faster than even light can catch. The expansion ensures that the edge is always moving away faster than we can approach. The paradox is that the more we travel outward, the more the universe grows ahead of us, ensuring that the edge forever retreats. Imagine a runner on a treadmill that constantly speeds up as they move forward. No matter how fast they run, the treadmill accelerates just ahead of them, always keeping the finish line out of reach. That is the situation we face with the universe. We can imagine going infinitely fast or infinitely far, but expansion guarantees that the finish line moves away at equal or greater speed. It is not a matter of determination, but of principle. The universe is designed such that horizons are not destinations, but shifting boundaries, always slipping beyond us. This paradox becomes even clearer when we consider that the universe may not have an edge at all in the traditional sense. If the universe is infinite, then there is no boundary to reach, and the pursuit itself is meaningless. Traveling infinitely far in an infinite cosmos is like trying to find the last number on a number line. You can always go farther. The paradox here is not just that the edge recedes, but that it may not even exist, making the very act of chasing it a contradiction. We are seeking a destination that is both unreachable and undefined, a finish line drawn by our imaginations but absent from reality. Even if we step back from the infinite and assume the universe is finite but unbounded, the paradox persists. A finite but unbounded universe, like the surface of a sphere, loops back on itself. Travel far enough in one direction and you eventually return to your starting point without ever encountering a wall. In this case, the paradox is that traveling infinitely far would not lead you to an edge, but simply bring you back home. The universe would offer no boundary, only endless paths that curve back on themselves. The more you try to reach the edge, the more you realize that it was never there. The paradox is not in the failure to reach the edge, but in the realization that the pursuit itself is based on a flawed assumption. The paradox also deepens when we consider the role of time. Suppose we could travel indefinitely, surviving across billions or trillions of years. Even then, the universe itself evolves in ways that erase the possibility of reaching an edge. Expansion accelerates. Galaxies vanish beyond horizons, stars burn out, and black holes evaporate. The longer we travel, the more the universe empties out, leaving only darkness and silence. The edge does not wait for us. It recedes and then disappears into meaninglessness. Even infinite persistence cannot overcome the fact that the universe is not static. The paradox is that eternal effort guarantees nothing, because eternity itself is working against us. This paradox reveals something humbling about the limits of exploration. Exploration on Earth has always been about reaching destinations, new continents, new planets, new frontiers. But the cosmos defies that framework. Here, destinations vanish as we approach them, horizons slip away, and boundaries dissolve into illusions. The edge is not a place we can conquer, but a concept that collapses under its own contradictions. The paradox shows us that the universe is not a landscape waiting to be mapped, but a dynamic, shifting reality that denies us the satisfaction of arrival. And yet, the paradox is not meaningless. It tells us something profound about our relationship with the universe. The fact that we cannot reach the edge does not mean the pursuit is pointless. On the contrary, it means the pursuit itself is the point. The edge of the universe becomes a symbol of curiosity, a reminder that there will always be mysteries beyond our reach. It teaches us that exploration is not about conquering final frontiers, but about embracing the endlessness of discovery. The paradox is humbling, but it is also inspiring. It means that wonder is infinite, that questions will never run out, that the horizon will always call us forward even as it slips away. This paradox also prepares us for a final reflection. If the edge cannot be reached because it is not a place but an idea, then perhaps the true edge lies not in the universe at all, but within ourselves, in our imagination, in our desire to push against boundaries, in our refusal to accept limits. The paradox of the unreachable edge shows us that the universe's greatest frontier is not physical, but conceptual. And so, to close this journey, we must turn inward to ask what the edge of the universe really means for beings like us, creatures who may never touch it, but who will always dream of it. The edge of the universe is one of those questions that refuses to let go of the human mind. We cannot help but ask it, even when every answer seems to remind us that the question itself may be flawed. Our species has always been driven by the idea of boundaries and beyonds. From the first humans who wondered what lay on the other side of the hills, to the sailors who crossed oceans in fragile ships, to the scientists who pointed telescopes at the sky, we are defined by the compulsion to seek edges, to find limits and then push past them. The edge of the universe is the ultimate expression of that drive, a frontier so immense that it challenges not just our technology, but our imagination. And yet, as we have seen, it may be an edge that does not exist in any physical sense. This realization could feel discouraging. If there is no edge, or if it is forever unreachable, what is the point of asking about it? Why does the question captivate us so much if it can never be answered through exploration? But perhaps that is exactly the point. The edge of the universe is not a destination to be found, but a mirror held up to human curiosity. It reveals that our need to explore goes deeper than practical achievement. It is not only about reaching new lands or discovering resources, it is about testing the boundaries of thought, stretching imagination into places where reality itself resists us. The edge is a story we tell ourselves, a symbol of the eternal gap between what we know and what lies beyond. When we reflect on everything that makes the edge unreachable, the speed of light, cosmic expansion, dark energy, entropy, human fragility, we begin to see that the edge is less about space and more about limits. It is the limit of light, the limit of time, the limit of perception, the limit of endurance. And limits, rather than discouraging us, are what drive us forward. Every scientific discovery in history began with an encounter with a limit, the limit of what could be seen, measured, or explained. The universe has always placed edges in front of us, and humanity has always responded not by stopping, but by asking better questions. In this way, the unreachable edge of the universe becomes the greatest gift of all, because it ensures that curiosity itself will never run out. The edge also challenges us to think differently about what exploration means. On Earth, exploration meant physically reaching new places. But in the cosmos, exploration may mean something else entirely. It may mean exploring through observation, through theory, through the imagination that allows us to glimpse realities we can never touch. The edge is not there to be crossed, but to be approached in thought, to remind us that science is not about conquering, but about understanding. The fact that we cannot reach the universe's edge does not diminish our quest. It elevates it, showing that knowledge itself is infinite, that there will always be mysteries left to contemplate. There is also something profoundly poetic about the idea that the edge is not out there, but within us. It is a boundary of perception, a horizon created by our position in space-time and the rules of physics that govern us. In this sense, the edge is a construct of the human mind, born of the way we interpret the cosmos. We invent the idea of an edge because we are wired to see the world in terms of beginnings and endings. But the universe, indifferent and vast, may not conform to those categories. Recognizing this is humbling. It reminds us that the greatest edges are not written into the stars, but into the way we think about them. The true frontier, then, is not a wall at the end of space, but the capacity of human thought to reach beyond itself, to stretch into the unknown, even when the unknown refuses to yield. This way of thinking transforms the paradox of the unreachable edge into a source of inspiration. If we could reach the edge, if there were a final boundary beyond which there was nothing, then curiosity would have an endpoint. The story of exploration would finish. But because the edge forever recedes, because it is perhaps infinite or illusory, curiosity itself becomes infinite. The fact that we can never reach the end means that there will always be another horizon, another question, another mystery. The unreachable edge ensures that discovery is endless. It guarantees that the human spirit of inquiry can never be satisfied, because there will always be more to wonder about. In this way, the edge of the universe is not a failure of exploration, but its fulfillment. It shows us that exploration is not about finishing a journey, but about sustaining a journey that never ends. To look up at the night sky and imagine an edge is to participate in the oldest human tradition, to see mystery and reach for it. Whether or not the edge exists, the act of imagining it shapes us. It drives us to build telescopes, to craft equations, to send probes into the void, to tell stories of what might be beyond. The edge of the universe, real or not, becomes a catalyst for creativity, science, and philosophy. It lives not at the boundary of space-time, but at the boundary of imagination. And perhaps that is the ultimate answer. The real edge of the universe is not a location we can ever travel to. It is the boundary between knowledge and mystery, always shifting, always receding, always inspiring. It is within us, in our minds and hearts, in the questions we ask and the awe we feel when we look at the stars. The physical cosmos may deny us the satisfaction of arrival, but in doing so, it offers us something even greater. A horizon that will never disappear, a mystery that will never fade. The edge is unreachable because it is eternal, and because it is eternal, it keeps us alive with wonder. So when we ask, will humans ever reach the edge of the universe? The answer is no. But in a deeper sense, the answer is also yes, because we already have. We reach it every time we imagine it, every time we stretch thought to its breaking point, every time we acknowledge the limits of what we can see and then push against them, we touch the edge. It may not be a place in space, but it is a frontier of mind. And unlike the physical cosmos, which one day may grow cold and silent, the frontier of curiosity is endless. As long as there are beings capable of asking questions, the edge of the universe will remain within reach, not as a destination, but as an eternal horizon of discovery. In this way, the story comes full circle. Humanity's desire to reach the edge of the universe is not about travel, not about conquest, not even about knowledge in the narrow sense. It is about imagination. The edge is the ultimate metaphor for the human condition. Small beings in a vast cosmos, always reaching for more, always chasing horizons that retreat as fast as we approach them. We may never set foot at the edge, but the pursuit itself defines us. The edge is not out there. It is within us as a reminder that we are creatures of wonder, bound forever not by the limits of the universe, but by the infinity of our own curiosity. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.